Find the area of the triangle with vertices at the 3 given points. So just to get us started here, I'm going to label these points. We can say that this is point A, point B, point C. So let's think about this a little bit first before we jump in. So we have 3 points here. Point A, point B, and we'll say point C is over here. How are we going to find the area of the triangle created by these points? If we connect our 3 points here, how are we going to find this area? Well, what we could do is use these 3 points to define 2 vectors. So let's let A be our initial point, and we can define a vector from A to point B. So here's our first vector, AB. And we can do the same thing connecting point A to point C. So here is our second vector, AC, with, of course, theta in between. Now, looking at this, we realize, hey, this looks an awful lot like a parallelogram, specifically half of a parallelogram. So to find the area of this triangle, I'll abbreviate, the area of the triangle is going to be equal to 1/2 the area of a parallelogram, or 1/2 the magnitude of the cross product defined by the vectors AB and AC. So here we go. The first thing that we need to do is find the vectors AB and AC. So vector AB. We have terminal minus initial. So I have 0 minus 2, 1 minus a minus 3, and 2 minus 4, which leaves us with the vector -2, +4, -2. Hey, we have a scalar multiple of 2 here, so let's pull that out to simplify our computation later. So this becomes 2 times the vector -1, 2, -1. So now we need to go ahead and find vector AC. So again, terminal minus initial. So we have -1 minus 2, 2 minus a minus 3, and 0 minus 4. And so we are left with the vector -3, 5, -4. So no scalar multiples here, but that's okay. So now we can take our vector AB and our vector AC, and we'll define the cross product of these 2 vectors. So here we go. We want to find the cross product of vector AB with vector AC. Now, don't forget about that scalar multiple of 2 in front. So we'll keep that on the outside of the determinant of our 3 by 3 matrix. So the second row is defined by the components of the vector AB, -1, 2, -1. And our third row is -3, 5, -4. And again, just be careful with your scalar multiple. We've got to keep that 2 on the outside of everything. So this will be, by the cross product, we have 2 times -4, which is -8, minus 5 times -1, which is -5, I hat, minus -1 times -4 is +4, minus -1 times -3 is +3, j hat, plus -1 times 5 is -5, and 2 times -3 is -6, k hat. So what are we left with here? We have 2 multiplied by, and now just be careful as you go about simplifying. So we have -8 plus 5 is equal to -3 I hat. We have 4 minus 3 is 1, but don't forget that negative in front, so that's minus j hat. And then -5 plus 6 leaves us with plus k hat. So the cross product is the vector 2 times the components -3, -1, 1. So now we want to take this vector and find its magnitude. So we have the magnitude of the cross product of vector AB with vector AC. And again, by the length of a scalar multiple, we can keep the 2 on the outside. And then we take the distance formula of the components. So we have negative 3 squared is 9, plus negative 1 squared is 1, plus 1 squared is 1. So we are left with 2 times the square root of 11. Now just be careful here. This is the area of the parallelogram, but we want the area of the triangle. So the area of the triangle is going to be 1/2 multiplied by the area of the full parallelogram, or multiplied by the magnitude of the cross product of vector AB with vector AC. So we have 1/2 multiplied by 2 times the square root of 11, and those 2's cancel each other right out. And so therefore, the area of this triangle is the square root of 11 square units. And this is our beautiful final answer.